Hello, I am Alfredo Apparel, and I would like to walk you through my team's senior design project, the Autonomous Vehicle Systems Research Laboratory Indoor Mapping Robot. The Indoor Mapping Robot is a system of systems. It exists as a network of individual subsystems working to accomplish different requirements of the overall system. It is divided into four main subsystems: autonomous mobility, camera control, image capture, and reality capture. I will now let my colleague Alberto discuss in a little more detail what the first subsystem, autonomous mobility, is all about.
The mobile robot is used as a base for the structure which houses the necessary sensors for data acquisition. By using a Python code that we developed, a telnet connection is established with the mobile robot. With the coordinates to the bottom left and upper right corner of the space, the program generates the points and the route that the robot will follow. The purpose of the route is to generate a 3D model which accurately represents the space with the fewest amount of stopping points. When the mobile robot is at a specified point, the Python code is intended to direct the PTZ cameras to capture images. To further discuss PTZ cameras and their role, my teammate Jonathan will now take over.
Thank you, Alberto. PTZ cameras can pan or tilt to various angles and can be controlled through the use of disk commands. A line of communication can be established between the cameras and the computer through the use of a wired connection. Each camera will have its own connection to the computer. Using a module known as PySerial, disk commands can then be sent from the computer to the camera, which are then interpreted into the proper movements. Currently, two BRC300 cameras are operated independently but simultaneously. Each camera will tilt from positive 20 degrees to negative 20 degrees in 20-degree increments. At each tilt position, it will also pan from positive 20 degrees to negative 20 degrees in 20-degree increments as well. This is done so that each picture taken has some amount of overlap, which helps improve the photo stitching process. To talk about the image capturing process, I will now hand it over to Yasmin.
Along with the PTZ and camera control function, the video capture capability was a necessary next step to take pictures from the PTZ camera. Using a Python-specific module called OpenCV, the live video capture and picture storage function was made possible. Using a device called Dazzle by Pinnacle, the PTZ would connect to a computer using an analog composite video source via USB. This feature would then allow the PTZ to be recognized by the computer and utilized in the Python script. From here, pictures would then be taken at specific angles, properly named and numbered, and then stored to a designated folder. Since the original PTZ pictures developed as stretched and distorted, an additional Python script included a lens matrix module to correct for lens distortion.
Once we obtain all the images using the PTZ cameras, we will create a 2D map of the facility by importing the point data from Omron's ladder scanner to AutoCAD using Python. The 3D models are created using ReCap. ReCap is composed of two different subcomponents, ReCap Pro and ReCap Photo. ReCap works under the principle of photogrammetry, which is obtaining information about a place through the process of interpreting photographic images. Here's Suri to talk more about how to create the models.
Thank you, Hector. The model consisted of 7 submodels that were generated from 505 pictures. Each submodel included anywhere from 30 to 90 pictures. With the use of the Autodesk ReCap, the 7 submodels were created and exported into the point cloud file format, which were processed in a program called Cloud Compare. Cloud Compare provides the ability to combine submodels, which is accomplished by pairing several points of commonality between submodels. Finally, the Unreal game engine was used to render the final composite model and provide more user-friendly way of exploring the virtual map.
The team decided to build a modular device which holds the cameras in place using 80/20 profiles. 80/20 is a versatile and modifiable building system. We know that our project won't end once we're done with it, and there will always be room for improvement, and we want these modifications to be as easy as possible. Here's Nathan to talk more about the specifics in the design.
The structure was designed with two main sub-assemblies, the platforms and the base. The platforms can be adjusted to the required height and can support devices including cameras. The 45-degree support bar was added to reinforce the platform while reducing the nodal vibrations within the structure. The base holds up the platforms and connects rigidly to the Omron LD90. The total weight of the attachment is 18 kilograms, which is within the 90 kilogram maximum. The entire robot has a low center of mass, and analysis confirms it would not tip while moving or stopping. We also made an assembly manual for easy construction and to show what materials were used for a project. This also so it can be assembled by future teams looking to use or modify our design.
Thank you, team. I hope you have learned something today and can appreciate all of the hard work our team has done to accomplish this. If you have any further questions or curiosity, feel free to explore our poster that discusses the project in more detail. Thank you.